Hello again. This is a video talking through AQA's GCSE Maths Foundation tier paper from a practice set released a couple of years ago, 2 or 3 years ago anyway, and it's based on the paper 2, which is a calculator paper. And so get your scientific calculator ready to use, and let's have a look at the first question. Question 1, what is 18 as a percentage of 72? Really, you wouldn't really need to use a calculator for this, but seeing as it is a calculator paper, I'll show you how you can use this calculator to do it for you. So 18 as a fraction of 72 would be 18 over 72. Then we can find that fraction of 100, because percentage obviously means out of 100. And so if we just get our calculator handy, use the fraction button, 18 over 72 multiplied by 100 comes to 25. So the answer to this one is 25%. This could come up on a non-calculator paper as well. Not that this is a non-calculator paper, but you could say that 100% of 72 is 72. Then from there we could work out what 50% was. Half of 100% is 50%. Half of 72 would be 36. And half again, to get 25%. So half is number 2. Half of 36 would be 18. And so that could be a non-calculator way of doing it. But I do digress because this is a calculator paper. But I just thought I'd mention briefly. Question 2, which one of these units is a unit of volume? Well, notice here it says units. I know normally AQA put in multiple choice and you just have to circle one, but it says units, circle your answers. So answers plural, not singular. We're going to have to be circling at least 2. So let's have a look what we've got so far. We've got centimetres cubed. Centimetres cubed is a unit of volume. Kilograms cubed, I'll be honest with you, I have no idea what that would be. It would have no meaning as far as I could see, because kilograms cubed would be something, for example, if you took your mass, your weight in kilograms, multiplied it by your neighbours, and then multiplied that by your mum's. It'd just be a meaningless number. It just would really make no sense. So that's just, where? What on earth? That just makes no sense whatsoever. Cubic metre. Cubic metre is very similar to cubic centimetre. It'd be written like this. That too is a unit of volume. And square metres is a unit of area. And so the two we want to circle are cm cubed and cubic metre, because these two are units of volume. So don't circle kilogram cubed or metre squared, circle these two. You need to circle them both to get the mark. Question 3, part A, which of these values could represent a probability? Well, there is a often forgot rule about probability. So all probabilities have a value between 0 and 1. So the probability scale only goes from 0 to 1. So 0 to 1. The probability can be anywhere from 0 to 1. Now on the probability scale, a probability of 0 would just mean something is impossible. If it's a 0 chance of happening, it's impossible. And the opposite of end of this is the other side with a 1, and opposite of impossible, this 1, the probability is 1, that represents certainly. certainty. So 0 is impossible. For example, you roll a dice and you get a score of 8. Or this one, certain, for example, the day after Friday will be Saturday, something like that. And so I've mentioned this because only one of these numbers is between 0 and 1. So only one of these numbers can represent a probability. So that's just worth highlighting. So have a look which number it is, see if you can spot it before I mention it. The number I'm looking at, and the number you'd have to circle, would be 0.8. This is bigger than 1, 6/5 is bigger than 1 whole, and minus 0.2 is smaller than 0, so the only one it could be would be 0.8. Part B, a fair ordinary dice is rolled once, and we're asked to circle the probability of rolling a 3 or a 4. And so how many sides on a dice are a 3 or a 4? That's going to be 2 sides. Two sides out of 6 have a 2 or a 4 on them. So the probability of rolling, oh dear, it's not 2 or 4, sorry, it's a 3 or a 4. You see, read the question, that goes for me as well. So 2 sides out of 6 have a 3 or a 4 on them. And so as a fraction, the number of ways you could roll a 3 or a 4, that could only happen in 2 ways. One way if we roll a 3, the other way if we roll a 4. And the total number of possible outcomes for rolling a dice has 6 sides, so there's 6 different possible outcomes. So the probability of rolling a 3 or a 4 is 2 out of 6, because 2 sides out of 6 have a 3 or a 4. So this one's 2/6. Question 4, simplify. So we've got x squareds and normal x's which can't be grouped. Things can only be simplified together into the same lump if it's the same letter and the letter is to the same power. So x squared is a different power to the normal x's. And so we need to simplify together the x squareds and then separately to the x squareds, the x's. To know if a term is a positive or negative thing, we have a look at the front of it. Whatever sign's at the front tells us whether to consider it as a positive thing or a negative thing. And if there's no sign at the front, you can always assume it's a positive. So looking at the x squareds, we start off with 12x squared, and we take away 8x squared. Because that 12 is positive. So you're best off starting, I'd suggest, with a positive thing, and then consider the negatives as what you're subtracting from that. So 12 squared x's take away 8 squared x's, we'd be left with only 4 x squareds. Now with the normal x's, we've got minus 5 plus 2. As I say, you could start with a positive 2x's and then consider those minus 5 as what you're taking away. So 2x's take away 5 is one way you could think of it. Another way we could think of this is we're starting at minus 5, just because that's our first number. And what we're doing is we're going towards the bigger end of a number line. So I'm just going to put some numbers on here. Don't just put them all on. Writing down an infinite amount of numbers would take quite a lot of time. So we're starting at minus 5, and this is going towards the positive end. Minus 5, minus 4, minus 3, minus 2, minus 1, 0. So if we start at minus 5 and go 2 in the positive direction, because that's 2 is positive, we'd end up minus 4, minus 3. So minus 5 where we're starting, add 2 would take us to minus 3. So that tells us how many x's we'd have overall. Minus 5 plus 2 would be minus 3 x's. Now it's just a case of putting these simplified parts together on the answer line. So simplified down, we'd have 4x squared minus 3x. And that's question 4 done. Question 5, we're having a look at Bobby stacking bricks, or Bob as he may prefer to be known. So he stacks 20 bricks in 1 minute. So the key word here is he assumes. So I don't know if this expression's around anymore, but when I were younger, and still occasionally now, I hear that assumptions make an ass out of you and me. The point I'm making is, ass out of you and me, assumptions can often be very wrong. I'm not saying all assumptions are wrong, but often assumptions can be wrong. So the key word here is assumption, that he assumes he can continue at the same rate. So maybe he's right, maybe he's wrong. We need to think about this in a real life context. So he says he'll stack 8,400 bricks in 7 hours. Let's give him the benefit of the doubt. Let's say he's right. So he can do 20 bricks in 1 minute. So if he carries on at the same rate, we could work out how many bricks he could stack in an hour. So how many minutes make an hour? The answer to that is 60. So if you multiply by 60, we'd find out how many bricks he stacks in an hour. 1 minute times 60 is 60 minutes, which I'll just put into brackets. That means an hour. So 20 times 60, let's see how many bricks he could stack in an hour, assuming he's right. 20 times 60 equals 1,200. So that's 1,200 bricks in 60 minutes, in 1 hour. So for 7 hours, to go from 1 hour to 7 hours, that's 7 times as long. So if you multiply that by 7, once for each hour he's working, that will tell us, in theory at least, how many bricks he reckons he can stack in 7 hours. So 1,200 multiplied by 7 comes to what he's saying. It comes to 8,400. $8,400 bricks in 7 hours. So he's assuming this in his calculations, and according to his assumption, he's right. I don't like to say any question's a trick question as such, but this is as close to a trick question as you might find, because it's so tempting to put yes, he's going to be accurate, because we've done the calculations and he seems to be right. But let's just think for a second in real life terms about Bob. So 20 bricks in 1 minute. If you just think about how many bricks that is, that means just 1 brick every 3 seconds. So he's not messing around. He's really going for it. That's a quick rate to stack bricks. Bricks aren't particularly light. His hands might get sore. Is he assuming he's going to have a lunch hour? What about the toilet? is he going to get tired? You know, Bob is likely going to be a human being. No, it doesn't say that he's a machine or a robot. So he's a human being, he's going to get tired. He's going to need to take a break, he'll slow down, he'll get bored, he might get a text. It's just not realistic. So actually, he's likely to stack a few bricks. So here's some working out, and you could put just another closing statement to back you up, like something to say, Bob would get very tired, or something like that. There's 1,000,001 reasons why he couldn't keep up that speed of working. If it was a case of a car driving along a motorway, which was quiet at night, then we could follow our assumption, because a car, assuming it's got plenty of fuel, can keep going at the same speed for a long time, because it's a machine. But Bob isn't a machine. So apply some common sense to this question. His assumption is a bit silly. So he's not going to stack as many bricks, he's going to stack fewer, because he'd get very tired very soon. So just think carefully with question 5. Question 6, we have to factorise 3 different things. This is a slight problem in terms of how you could fall into a trap of thinking it would be a double bracket, but it's not. It's just going to be one thing we're going to factorise out. If it was an x squared or a y squared, it might be a case of one of these here, one of those types of factorisations. 2 main reasons why it's not going to be. There's no x squared or y squared. Secondly, it's early on in the paper, and so typically factorising quadratics is going to be something they put towards the end of the paper, or at least the second half of it. So think the examiner might be being on the nice side rather than on the evil side now. So to factorise, it means we're putting into brackets. So all the letters are different, x, y and z, so there's no letters common in each group. What we can do though is have a look at these numbers, 18, 42 and 30, and we need to think, what's the biggest number we can divide all of these numbers by? Always pick the biggest. So 18, 42 and 30, you can check on your calculator as well if you'd like to, will all divide by 6. Common factor of 18, 42 and 30 is 6. Nothing else is in each, there's no letters common in each, and so anything we can put on the outside of a bracket is a common factor of 6. Secondly, now we need to ask, how do I end up with 18 if I've got 6? What do I multiply 6 by to get 18? The answer would be 3. 6 times 3 is 18. But of course we don't just want 18, we want 18x, so we need to include an x on the inside. Next is a minus sign, so put a minus sign down ready. What do we multiply 6 by to get 42? 6 times 7 would be 42. But because we need to end up with a y, we need to include a y here as well. Next one is a plus, so put plus down. What do we need to multiply 6 by to get 30? That would be 5. And in the same way as before, because it's not just 30, it's 30z, we need to include a z at the end of a 5. So that's our fully factorised answer for question 6. Question 7. An experiment has 4 different outcomes, and we need to circle the probability of outcome B. Okay, for any experiment, if we add up all the probabilities for any single experiment, they'll always add up to 1. And so 0.1 plus whatever B is, plus 0.2 plus 0.3 will all add up to exactly 1. So we can neaten this up and simplify it down somewhat by collecting together the numbers. 0.1 plus 0.2 plus 0.3 would give us a total of 0.6. So 0.6 plus b needs to add up to 1. So what number, when you add 0.6 to it, would give us 1? It's going to be 0.4. What we can do though is to have b on its own. We can swap this 0.6 to the other side of the equation, and if we swap side, we swap the sign. In this case, the plus becomes a minus. And so b is just 1 take away 0.6. Use your calculator if in doubt. And we get 0.4. So the probability of outcome B is 0.4. That's the one we need to circle. And that's question 7. Question 8 involves an isosceles triangle ABC, and one angle we've been given. So the angle at A is 56 degrees. We've not been told what C is or what B is, and so it's our job to try and find out what C and B could be. So what I suggest we do first of all is just have a think about what isosceles means. So a triangle is isosceles if two sides are the same length, and two angles are the same. So this one's 56. There's going to be a few possibilities of what C and B could be. So let's have a look at what I would think is maybe option 1. So possibility 1, angle A is the same as angle B. That would be an isosceles triangle if the two bottom ones are equal. And so if that were the case, what we'd have is this one's 56 degrees as well. So in that case, because we're only interested about possible values of angle B, in this scenario angle B would be 56 degrees. This one at the top, if you wanted to work it out, remember angles inside a triangle add up to 180. Not that we care about angle C. Angle C as in the angle, not angle C, the lovely place in Wales. Angle C here would be 180, take away 56, take away 56, which would be 68, in case you wanted to know. So that's the first possibility. Angle B is the same as angle A, which is 56 degrees. But here's another possibility though. The other possibility we've got is that angle A and angle C are the same. And so if this were the case, then angle C up here would be 56, and angle B would be 180, take away 56, take away 56, which would be 68 degrees. Basically the same as the first possibility, but the 68 and the 56 have swapped over. So possibility 2 is that angle B is 68 degrees. And there's another final possibility as well, and this possibility is that angle B is the same as angle C, and angle A is the odd one out. And so we could work this one out by thinking how much would these be together. Well, angles in a triangle add up to 180 degrees. And so 180 take away 56 would tell us what these two are combined. So 180 take away 56 would leave us with 124 degrees. So that tells us that these two angles together are 124. But if these two were equal, then that 124 degrees would be shared equally between them both. So each one would be 124 divided by 2, which your calculator should tell you is 62 degrees. So third option is angle B could be 62 degrees. So we've got three different options, possibility 1, 2 and 3, and we've got three different corresponding options for what angle B might be. So the answers are angle B could be 56, it could be 68, 68, or it could be 62. So 56, 68 and 62 are what we put down for our answers, and this is the working backing us up. Question 9, it says complete this pay statement. Looks an awfully big question, but it's not as bad as it might look, because pay per hour and hours that have been worked, this is quite easy to work out what the pay would be. So if you work 35 hours and you get paid £14.30 for each one of those hours you've worked, we can calculate this total by just doing the number of hours worked multiplied by the hourly rate. So the first row would be 35 multiplied by £14.30. That comes to £500.50. The second row, 7 hours, £18.80 per hour, that would be 7 multiplied by £18.80. So 7 times £18.80, we can do that as well. And let's see what we get. That means £131.60. And finally, 4 hours at £21.45 an hour. Multiply those together. And for that, we'd get £85.80. So for total pay, with these values added together. So considering it's a calculator paper, we may as well use the calculator. So £85.80, which I've already got here, plus £131.60, plus £500, not 5,000, and 50. That comes to £717.90. Now deductions just mean what's taken away from the wage. Deductions are what is subtracted before you get paid. And so tax is deducted and national insurance is also deducted. So this line here wants the total deductions. It means the total of how much has been taken out of your wage. So for total deductions, these two things are for deductions. That just means the total of these two values here. It's got nothing to do with this yet. So the total deductions will be £64.80 plus £85.60, and that comes to a total of £150.40 of deductions. And the final part for take-home pay is the total pay subtracted from the total deductions. So the total pay is what we had earlier up here. The total deductions is what we've just worked out on the above line. And so £717.90 take away £150.40 gives us a total take-home pay of £567.50. There you go, 567.50. And that's question 9 done. Question 10, work out 5 1/4 plus 1/2 multiplied by 2/3. Give your answer as a mixed number. Now, how hard this question is, I believe, depends on two things: how good your calculator is and how used to using your calculator you are. So having a calculator isn't enough. A calculator won't do all the hard work for you because you need to practice using it yourself to get the most out of it. Now, I actually tried this question myself without realising it was a calculator paper, and I thought, this seems hard for question 10. Then afterwards I remembered it was a calculator paper. So if you have a calculator like this, for example, and you know how to use it, this question becomes rather straightforward. First of all, 5 1/4 is a mixed number. You can't just do it like this. You can't just put in 1/4 and skip back and put a 5 at the beginning. If you press equals, 5 1/4 isn't the same as 1.25. What you need to do for this part here is to do the mixed number function on your calculator. So in this case, you can do Shift fraction button, and then you get 5 1/4, so it can be typed in just as it appears. And the rest of it you can type in as it appears exactly in the question. So plus sign, then a half, multiply, and 2/3. And so this screen here looks exactly like this one here, and we've used our mixed number function as well. So press equals, we get 67/12. So just for putting 67/12, that would be 1 mark. But we want the answer as a mixed number. So how many 12s go into 67? We can fit 5 with 7 12s left over. But you know what? Your calculator can even do that for you as well if you know how to use it properly. We can convert from a top-heavy fraction to a mixed number on this calculator by pressing Shift and the conversion button just above the delete function. It changes it for us to 5 wholes and 7 12ths remainder. And so that's our final answer as a mixed number. 1 mark for the top-heavy fraction, second and final mark for the correct mixed number. Question 11, we have a rectangle with 6 masses inside it. In fact, there's 2 rectangles, rectangle A and rectangle B. And we need to show that the sum of the 6 masses is 2007.3 kilos. So we want to show that the 6 masses weigh something in kilograms, which is fine, we can do that. But not all the units are in kilograms. These ones are 1 kilogram and 5 kilogram, so they're fine. It's the others we need to think about converting. So what we need to know for this question is that 1 kilogram is equal to 1,000 grams. And also what we'll need to know is that 1 ton is the same as 1,000 kilograms. So both these relations are in the form of where one number is a 1, the other number is not 1. So 1 kilogram, 1,000 grams, and 1 ton, 1,000 kilograms. When a relation is in this form, where one number is 1, the other isn't, we can change from one unit to the other by multiplying or dividing by the number that isn't 1. So for example, to change from kilograms to grams, we're going from a small number to a big number, so we'd have to make it bigger, so that'd be timesing by 1,000. Same with going from tons to kilograms. The ton number will be smaller than the kilogram number. 1 is smaller than 1,000. So to change those units, we'd be timesing by 1,000. Going the other way, we do the opposite thing. So for example, changing from grams to kilograms, going the opposite way, opposite thing, opposite of timesing by 1,000 would be to divide by 1,000. And opposite of timesing by 1,000 again here, exactly the same, to change from kilograms to tons, therefore we'd have to do dividing by 1,000. But as I said slightly earlier, for part A we want all our units to be in kilograms. And so where we see grams, we need to change the grams to kilograms. And so what we need to do is to change these grams to kilograms by dividing them by 1,000. And so what we can say here is that the total of the masses I'll come back to that point in a second. The total is going to be 1 kilogram plus 5 kilograms plus 250 grams plus 750 grams plus 300 grams and plus 2 tons. So what we may as well do is just group the grams together. So 250 grams plus 750 plus 300, we can add these together. So 250 plus 750 plus 300. Check on your calculator if you'd like. That will come to 1,300 grams. We can then convert that into kilograms by dividing it by 1,000. So, like we said here, from grams to kilograms we divide by 1,000. So in kilograms, 1,300 grams will be 1,300 divided by 1,000, which will come out to be 1.3 kilos. And so the sum of all these weights in grams, 250, 750 and 300, actually comes to 1.3 kilograms. So we now need to work on the tons. So we need to change from tons to kilograms. To go from tons to kilograms, we have to multiply by 1,000 rather than dividing. So if we multiply 2 by 1,000, it would tell us that 2 tons is the same as 2,000 kilograms. So we can now just put everything in terms of grams. So 1 kilogram is 1 kilogram, 5 kilograms, again, still 5 kilograms, but these weights in grams, we've just changed here into kilograms. So the kilograms stayed the same because we're happy in the kilogram units. These three here, we added together over here, and we showed that these come to a total of 1.3 kilograms. And finally, the 2 tons over here, we said was 2,000 kilograms. The only thing left to do now is to add all of these things together. So 1 plus 5 plus 1.3 plus 2000 comes to a total of 2007.3 kilograms, like we wanted to prove all along. And so that's proven that they do add up to 2007.3 kilograms. So we've proven it. So we've done for part A. The key there is knowing these conversion factors, kilograms and grams, tons and kilograms. Now for part B, it says 3 of the masses are moved from A to B. The mean of the masses in B is now 2.1 kilograms. So it's worth just reminding ourselves how we calculate the mean. So the mean of something, in this case the mean of the masses, will be the total of the masses divided by the number of masses that have moved. So let's see what we can put into this equation for the mean. So we're actually told a few things already. We're told that the mean in B is now 2.1. So if we substitute 2.1 for the mean, because we've been told that's what it is, we can make a bit more progress. The total of the masses, that's what we're trying to find out. We don't know what the total is, so let's just call it T for total. And the number of masses, in other words, how many masses moved, we've been told that 3 masses moved across. So 2.1 kilograms equals the total divided by 3. And so we can work out what the total is on its own by just rearranging this equation. That 3 is dividing the t above it. To have t on its own, we need to get rid of this 3. That 3 is dividing the t. Opposite of dividing by 3 would be to multiply. When we swap side, we swap sign. So t would equal 2.1 multiplied by 3. That tells us the total weight in B must be 6.3 kilograms. And so the 3 masses that move, we need to find 3 masses which add up to 6.3 kilograms. And so we can do that fairly easily. That's 5 kilograms. That's 1. 5 plus 1 is 6. So I need 0.3 of a kilogram. From before, we showed that 300 grams, we can divide that by 1,000 to get it into kilograms. 3,000 grams would be 0.3. So the 3 masses that move, the 3 masses that add up to 6.3, will be the 1 kilogram, the 5 kilograms, and the 300 grams. Because those 3 weights are the only ones that add up to 6.3. Question 12. It says I'm thinking of a number, it has 2 digits, and it's 3 more than a number that is both a square and a cube number. That's the big clue here. It then says, is the number I am thinking of a prime number? And to tick a box. The main thing is, we're told that it's 3 more than a number that's both a square number and a cube number. So what we need to do here is be thinking of what the square numbers are and what the cube numbers are. And see what number is both square and cube. So square numbers, your first square number is 1 times 1, which is 1. 2 times 2, which is 4. Of course, I'll just mention you can do these on a calculator very easily. So first one is 1 squared, which is 1. 2 squared is 4. The next one is 3 squared, which is 9. So if you're not sure what the square numbers are, or you think you've forgotten, or whatever, you're not too confident, you can use a calculator just to help you out. Ideally, you should know the square numbers, including up to 12 times 12, if possible. 6 times 6, 7 times 7 is 49, 8 times 8, 9 times 9, 9 squared is 81, 10 times 10 is 100. 11 times 11 is 121, it looks like I'm running out of space. Cube numbers, we can do in the same way, but only, instead of to the power 2, we've got to the power 3. So the first cube number is also 1. Second cube number is 2 cubed, 2 to the power 3, which will be 8. Next one, be 3 cubed. That means 3 multiplied by 3 multiplied by 3, which is 27. Then 4 cubed, 4 to the power 3, will be 64. The next one, 5 to the power 3 equals 125. I could keep going, but if I kept going, my square numbers would be falling behind quite a lot because my cube numbers have already got bigger now. 125 is bigger than 121. So let's just scan both lists, both the square numbers and the cube numbers. Is there any number we can see in each list? Any number that's both square and cube. Hopefully you'll spot that 64 is in each list. For that reason, that shows us that 64 is both square and cube. So I'm just writing that down to be clear. 64 is a square and a cube number. But of course, this person wasn't thinking exactly of a square and a cube number. It was saying they were thinking of 3 more than that number. So 3 more than a number that's both square and cubed. Well, a number that's both square and cubed would be 64. But we want to be thinking of 3 more than that. Then we've got the person's number. So 64 plus 3. Plus 3 because it says 3 more. Will be 67. So the number this person's thinking of must have been 67 because it's 3 more than 64 and 64 is both square and cube. So is the number I am thinking of a prime number? So is 67 prime? I'll show you a little calculator trick which could help you. Essentially 67 is actually a prime number because we can't divide it by anything apart from itself and 1. So it's prime. I'll show you though how you can check on a calculator if a number's prime or not. On this calculator specifically. Press the number you want to check if it's prime or not and press equals. Then we can do the prime factorisation of that number. Now if nothing happens, it means that the number itself is already prime. So shift, fact, nothing's happened. Whereas if you picked a number that wasn't prime, for example 6, and did shift, fact, we'd split it into its prime factors. So if a number's not prime, shift, fact, splits it into primes. If it's already prime, nothing happens. So I'll just show you that again. 67, press equals, then shift, fact, nothing happens, therefore it's prime. Or by trial and error, you wouldn't find anything you can divide 67 by, apart from 1 and 67. So yes, 67 is prime. Question 13, we're talking about an election. And it says, before an election, 23% of people said they would vote for party A, 9% said they'd vote for B, 20% said they would not vote. So all those people voted as they said they would, and the rest of the population actually voted for A and B in the ratio of 1 to 2. So just writing this here, the rest voted A and B in the ratio 1 to 2. First of all, let's work out what percentage of the population we can account for up here. So we've got 23% voting for A. Let's do a little list actually, just total votes. So we've got A, B, neither. So just draw that in just to anticipate our findings. Anyway, before the election, 23% said they'd vote for A, 9% B, 20% said they wouldn't vote. And so we can add up these figures here to work out what percentage of the population these people are. 23 plus 9 plus 20 comes to 52%. And so this bit represents 52% of the population. So when it mentions about the rest of the population actually voting for A and B in the ratio 1 to 2, the rest, in this case, will actually mean the other 48%. If 52% voted like they said they would here, 100% is everybody, so 52% voted this way. How many percentages left? It's 100 take away 52, which should be 48. And so the remaining 48% of people must have voted for A and B in this ratio. So one lot of people voted for A, two lots voted for B. So this is a fairly standardish ratio question. Now we're splitting this percentage into a ratio 1 to 2. So one lot for A, two lots for B. That's a total of 3 different shares, 3 different pieces. So we're splitting 48% into 3 pieces. So we could do 48 divided by 3 now, which is 16. So that tells us that each share is worth 16%. And so of these other 48%, those that voted A was 16%. Those that voted B, 16 times 2, was 32%. As a double check, 16 plus 32 does give us 68. So now we can work on these grand totals. So for A, let's see, 23% said they voted for A, plus we worked out of the rest of the population, we had another 16% voting for A. So the total votes for A would be 23% plus 16%. 23 plus 16 would come to 39%. So 39% of the population voted for A. Now for B, initially 9% of people said they'd vote for B. And also, of the 48% of other people, we calculated that 32% voted for B as well. So that initial 9% plus this other 32%, that would come to a total of 41%. So 41% of people voted for B. And that comes to 80%, so 20% is left, which is no surprise because it says here that 20% of people said they would not vote. So people who didn't bother voting were 20%. So who got most votes Well, it's definitely between A and B, and the leader is B, because 41% of votes is slightly higher than 39%. So therefore, we can say B got the most votes. Moving on to part B, we're told that 612 people didn't vote. So it says how many people did vote. So let's have a look at this. Just going back to part A, 20% said they wouldn't vote. So 20% of people didn't vote, and we're told that the people that did not vote was 612 people. So from these two pieces of information, we can work out that 20% of people must be these 612 people. So it's now saying how many people did vote. Well, if 20% of people didn't vote, what that means is the other 80% did vote. And then my writing's going a bit crazily downhill. I'm trying to make room for this bit at the top. So the other 80% of people did vote. So we know what 20% of people is. What we could do with working out now is how many people 80% would be. Because 80% of the people, that's representing the people that did vote. People that did vote is the 80%. So how can I go from 20% up to 80%? What would I have to multiply 20 by to get to 80? Well, 80% is 4 lots of 20. 80% is 4 times bigger than 20%. And so if we're making this side 4 times bigger, to keep the balance right, we need to do the same over here and make this number 4 times bigger too. And so 612 multiplied by 4 will tell us 80%. So 612 times 4, 2,448. So how many people did vote? 80% did vote, and that's a total of 2,448 people. And that's our final answer for part B of question 13. Question 14 now. 2 rectangles are shown on the grid, and we're told that the rectangles are congruent. So congruent is one of these fancy mathematical words. All it means is identical. Same shape, same size. And so that begs the question, why don't they look the same? Well, that can only be because this one's like stood up, this rectangle stood up, this one's laid down on its side. We need to work out the values of A and B, so what we could do with knowing is the length and the width of this rectangle. And so if we have a look at this one here first, and just take the x-coordinates. The x-coordinates are the numbers that come first. So -6 is here. This one's -2. And so if you just imagine a line between. So between -6 and -2, -6 and -2, we could calculate the change in x. From -6 all the way to -2, how much is x changed by? The difference between two numbers we can work out by doing one subtracted by the other. And so hopefully you could maybe even count that it's going to be 4, -6, -5, -4, -3, -2. There's a difference of 4 between -2 and -6. And in the same way, looking at the y values down here, y is -1, and at the top of a rectangle, y increases to 2. So between these 2 points, y's gone from -1 all the way up to 2. -1 to 2 is an increase of 3. 1, 2, 3. And so that must mean that the rectangle is also 3 wide. So we can add these measurements onto this triangle now. Oops. It's a bit off center. I'll try and get it nice and accurately drawn on. So this length here, from end to end, is 4, because that coordinate's changed from -6 and gone up to -2. And we just said that the width of a rectangle was 3. And this triangle is identical to this one because this one has been rotated over. And so if I just grab this one now and rotate it, and move over to here, we can then hopefully see that this one now is 4 high and is 3 wide. That 3 is a 3 written on its side, so it looks like a W. So I'll just get rid of that so it's clearly a 3. It's because I rotated the number 3 as well. So I'll just get rid of this and put in that it's a 3. So A is all the way over here on the top right corner, and A is the x coordinate. So first we'll start off at 4, and then we go 3 along. So 4 plus 3 means that A would actually be 7. And B is the y coordinate. So down at this point here, y is 4. So if we go 4 higher, that takes us to 5, 6, 7, 8. And so B would have to be 4 plus 4, which is 8. Not the easiest of questions, to be honest, at all. But ultimately A would be 7, and B would be 8. You would get some marks along the way though if you correctly worked out the dimensions of a rectangle. So getting something is better than not understanding or not attempting the question at all. Question 15, we have a Venn diagram. So E stands for everything, and we've got 2 circles that overlap. M stands for multiples of 3, F stands for factors of 24. So we can do these as a list. So if I call M multiples of 3, this circle over here represents the multiples of 3. So I'm just going to try and draw around that as best as I can, which as you can see isn't particularly great, but still. And factors of 24 is the circle on the other side, the circle on the right hand side. And where these 2 circles overlap, that represents numbers that are both multiples of 3 and the factors of 24. But let's just think about the numbers from 1 to 12, which ones would be a multiple of 3? Well, multiples of 3 just means your 3 times table. So the first one would be 3, 6, 9, and 12 itself. Any higher we don't need because we're only going from 1 to 12. Now factors of 24, all that means is what numbers we can divide 24 by. So the smallest thing we can divide any number by is 1. Anything divided by 1 just stays as the number itself. Higher than 1, we could have 2. So 2 is a factor of 24. And 24 divided by 2 is 12. We can also divide 24 by 3, which gives us 8. And finally, we can divide 24 by 4, which gives us 6. And so we don't want 24 as such because we just want the numbers from 1 to 12, so I'll just scribble that one out. So factors of 24, which are between 1 and 12, are all these numbers here. So we've got 1, 2, 3, 4, 6, 8, and 12. And so if we were to list the numbers from 1 to 12, just down here, almost running out of space, got there just about. So multiples of 3, we can use a yellow colour for. Factors of 12, we can use this green colour for that circle. And so if we just underline multiples of 3, 6, 9, and 12, and then in green, the factors of 24, we have 1, 2, 3, 4, 6, 8, and 12. The numbers that have been underlined twice, the numbers with both a yellow and green underline, represent the numbers that are both multiples of 3 and factors of 24. So the numbers that have been underlined twice are the numbers that should go in the overlapping bit of a circle. And so in the overlap would go 3, 6, and 12. 3, 6, and 12 are factors of 24 and also multiples of 3. And so we've thought about 3, 6, and 12, so we can put those to one side and just forget about them now. Now, which numbers are green only? We've got 1, 2, 4, and 8. So in any order, 1, 2, 4, and 8 go into the green circle, which is for factors. So 1, 2, 4, and 8 we've dealt with. The only number which is yellow only a multiple of 3, is the 9. So the 9 is on its own in that bit. So we've dealt with the 9. Now the numbers that haven't been underlined at all means the ones which aren't multiples of 3, nor multiples of nor factors of 24. So these don't belong in any circle. And so these 4 numbers left go on the outside of the circles. They can go anywhere within the outer rectangle as long as they're not going inside the circles. And so that's the Venn diagram completed. So for part B, I've just done a carbon copy of that previous Venn diagram so we can refer to it for this question. Part B says to complete the table to show how many numbers are in each part of a Venn diagram. So first of all, the factors of 24. So which factors of 24 are also multiples of 3? That's the overlapping part. So 3, 6, and 12, that's 3 numbers. 3 numbers are in the overlap. Factors of 24, but not multiples of 3, that would be only these numbers here. So we've got 1, 2, 4, and 8. So there's 4 different numbers that are factors of 24, but not multiples of 3. And so altogether, that's 7. 3 plus 4 gives us 7. Now the ones which aren't factors of 24. So all these numbers around here aren't factors of 24. So which aren't factors of 24 but is a multiple of 3? That's just for number 9 on its own here. It's outside the factor circle, but it is a multiple of 3 on its own. So it's just one value there, which is not a factor of 24, but is a multiple of 3. For numbers that aren't a factors of 24 and aren't multiples of 3 either, the ones that don't belong in either circle, are these 4 values on the outside, 5, 7, 10, 11. So there's 4 numbers on the outside. That gives us a total for this row of 1 plus 4, which equals 5. As a double check, this column adds up to 12 like it should do. 7 plus 5 is 12. So just make sure these columns add up as they should. 3 plus 1 is 4, and this one 4 plus 4 equals 8. So that row adds up to 12, and the column adds up to 12, and so that's question 15 complete. Question 16, we've got a diagram with a square and a circle inside the square, and we need to work out the shaded area. So we're told what the radius of this circle is, which is good news. So we're told that the radius is 7. Now the radius of a circle just means from the middle to the outside. So for this circle, it's 7 centimetres. We need to know the formula for the area of the circle. So pi relates to circles, and pi relates to food as well. So chicken pies, delicious. Apple pie for dessert. Apple pies are 2. It's a silly way you can remember that circumference is pi times diameter, area is pi r squared. Chicken pie is delicious, apple pies are 2. Simon Ferris, I think, taught me that one. Simon's now outside of the country. Anyway, never mind. The one we're wanting for the area, the formula for the area, is this one here. So we'll come to the circle in a second. The easier shape to deal with would be the square. So if this circle is 7 centimetres in radius, so from the middle to the outside is 7, then all the way along its diameter would be double the radius, which would be 14. The diameter just means from one end to the other going through the middle, and that is also the length of the square. And so this square must be 14 long, and because a square has all the sides of it the same, the square must also be 14 centimetres high. So the area of the whole square that's just the length times width. But for a square, the length is the same as the width. So in this case, length times width is 14 multiplied by 14. 14 squared, which we can work out easily enough on this. 14 multiplied by 14 gives us 196 centimetres squared. But we just want the shaded area, which is the whole square with this circle taken out. So the circle looks like it's been cut out and is missing. So what we need to do next is work out the area of the circle. That's going to be pi multiplied by the radius, which is 7 squared. So pi times 7 squared, we can do on the calculator. Pi multiplied by 7 squared. The answer it might give us is in terms of pi, so that's 49 pi. As a numerical value, we can press this button to convert it to a decimal. And so to a sensible degree of accuracy, to one decimal place for example, this would be 153.9 square centimetres. And so the shaded area will just be the area of the whole square, which is 196 subtract the area of a circle, which is 153.9. And the difference will just be whatever's left around the outside. And so 196 take away 153.9 would come to 42.1 square centimetres. And that's our answer we can write down. 42.1. And that's question 16 complete. Question 17, it mentions about a sequence. So the nth term of a sequence is 3n squared. And we need to work out the value of the 15th term. So if there's nothing in between the 3 and the n, does that mean 3 multiplied by n squared, whatever n happens to be. So n just means the nth term. So for part A we need to work out the 15th term, in which case n would be 15. N is the term number, so the 15th term means we can just use the value of 15 in place of n. And so 3n squared becomes 3 multiplied by 15 squared, because we're saying now that n is 15. So we can try this on our calculator. 3 multiplied by 15 squared, and we get an answer of 675. So that's the answer to part A. For part B, again the same sequence, 3n squared, and we're asked now what is the position of a term in the sequence that is the first one with a value greater than 1000. I could show you a way of doing this algebraically using square roots, but I think the easiest way may be just a case of trial and improvement. Just trying different values of n and seeing what will work. So we started off before with 15. When n was 15 we had 675, so let's try when n is 16. 3 multiplied by 16 squared, what would that be? 768. Getting closer, but not there yet. So try n equals 17. Just go back and change it to 17 squared. Getting close to 1000, but not there yet. Try n equals 18. Three times 18 squared. Be 972. So it's looking very likely it'll be the 19th term. So when n is 19, three times 19 squared will be 1083. So that's the first one that has a value greater than 1000. And the position of the term is it's the 19th term. When n is 19, we get the first value that's bigger than 1000. And so our answer is either 19 or just something along the lines of saying it's the 19th term. Question 18, we've got x to y to z in the ratio 2 to 3 to 5. So we want to circle the value of x as a fraction of x plus y plus z. Now, whatever comes after the of, when we're talking about fractions, tells what the bottom number is, what the denominator is. So x as a fraction of x plus y plus z could be written like this. X is on top as a fraction of x plus y plus z, which goes on the bottom. And so the value for x is 2. For y, we've got 3 parts, and for z, 5 parts. And so x plus y plus z would be the same as 2 over 2 plus 3 plus 5. Because x has, in the ratio simplified down, x is given by the value 2, y has been given by the value 3, and z has been given value 5. And so we can get the calculator to do the legwork for us. So on the top is 2, on the bottom 2 plus 3 plus 5. Press equals, we'll get 1 over 5. So that simplifies down to 1/5. And so that's the one we need to be circling for question 18. Question 19, we have to circle the number that has an integer power of 4. So what on earth does an integer mean? Well, the word integer just means whole number that can be negative. So it doesn't have to be positive, it can also be negative. So integer powers of 4 just means things along the lines of 4 to the power 1, 4 to the power 2, 4 to the power 3, and so on. And even 4 to the power minus 1, 4 to the power minus 2. So as long as this power of 4 is a whole number, that is known as an integer power of 4. So we can try these values here. 4 to the power 1, let's see what that gives us. Anything to the power 1, by the way, is just the number itself. But if in doubt, we can try it here. So 4 to the power 1 is 4. 4 squared, 4 to the power 2 is 16. And that's the one we can already see on the list. 16 is a power of 4 because it's 4 to the power 2, and 2 is an integer. So for part A we can just circle 16. And for part B of question 19, it says work out this as a power of 5. I'll give you 2 different ways. The first way, if you can remember laws of indices, if the thing you're raising to the power is the same number or the same letter, in this case all these ones with powers on are a 5, then what you do is when you're dividing, you subtract that power. So we start with 12. Because you're dividing that, we would take away that power of 3. And when you're multiplying, you add the little number on. So when you're dividing, you take away the little number. When you're multiplying, you add on the little number. Assuming that you're talking about the same big number or letter that's got the power on it. So this one here, 12 take away 3 is 9, plus 2 is 5 to the power 11. So that's one we'd need to circle. If you forget that rule of powers about taking them away when you're dividing and adding the little numbers when you're multiplying, you could, for this one, do it the long way on the calculator. So if we use the calculator here, we can just type these values in. So 5 to the power 12 divided by 5 to the power 3 multiplied by 5 to the power 2. So that's the answer on the calculator. 48828 125. That's what it equals. And then you can just see which one of these options matches to this. And so eventually you'd come across 5 to the power 11. And if we do 5 to the power 11, it matches exactly. And so 5 to the power 11 is the only one that matches to this calculation if you try it on a calculator. So that's the second way you could think about answering this question. Question 20, we've got a compound interest question. So it says £4,000 is invested at 1.5% compound interest. We need to show that the value of the investment after 2 years is £4,120.90. If you're not sure where to begin with compound interest questions, bear in mind compound interest means the interest is very likely to change each year. So you can't say it's simple interest. So you need to consider each year separately to each other year. So probably the simplest way of understanding that would be to do it as a table. It's not the only way, but it's the way I'm suggesting we try it here. So we can have columns for the year, the starting value, the interest rate, because some questions it can change, the interest earned based on that rate, and then the end of year total, which is what you started with, plus the interest earned on top. And so we're starting off with £4,000, and the interest rate is 1.5%. So we can calculate the interest by doing 1.5% of 4,000. Percentage means out of 100, so 1.5% means 1.5 out of 100. So it's that percentage of the initial 4,000, which is 60. So the first year we get £60 interest. So the end of year total will be the £4,000 we started at the beginning of that year, plus the £60 interest, which comes to £4,060. So that final amount at year 1 is what we're going to begin with at the start of year 2. So we do the same process again, this time with just a slightly higher starting amount. The interest rate isn't going to change, it stays at 1.5. So the interest in year 2 is now going to be 1.5% of 4,060. So it's the same percentage, so we can leave that here, but this time we're talking 4,060. 1.5% of 4,060, which now is 60.9. That represents £60.90. So slightly more interest. Like I said, because it's compound interest, this interest will change from year to year. So now for year 2, the end of year total is 4,060, what we started with at the beginning of year 2, plus the £60.90 interest. So add those two values together, and we should get, well, let's see, so £60.90 plus 4,060. We get £4,120.90, which is what we wanted to show in the first place. After 2 years, we've ended up with £4,120.90. So that's it for part A, and part B carries on in the same way. So in part B, the interest rate for the third year falls to 1.4%. And in the fourth year it falls further down to 1.35%. And so what we can do is we can use the table we had before. If I just put it to one side, we can use this table now. I've copied down what we had before, so this is nothing new, this is just what we had from the previous part A. And we can carry it on for the third year and the fourth year. But just pay attention to the fact that in the third year the interest rate falls to 1.4. So let's put that in before we forget. Then in the fourth year it falls again to 1.35. So what we're looking at here is the interest rate for year 4, sorry, the interest earned for year 4. We're going to be comparing that against the interest for year 3. So these are the two boxes we're interested in. But for now, just carry on as we were doing. So end of year 2, we had that value. So that'll be our starting value at the beginning of year 3. Now the interest is going to be 1.4% of this amount. So the next thing we need to do is 1.4%, which means 1.4 out of 100. That percentage of 4120.90. And we get £57.69. We may as well round off to the nearest penny, because in real life banks either pay you a penny or they don't. So that's going to be £57.69p. So then the end of year total will be £4,120.90 plus the £57.69. So let's add this together. So that added to £4,120.90. That gives us a total of £4,178.59, again to the nearest penny. 4178. And then I think it was, 59. Now for year 4, the starting value at the beginning of year 4 will be the end value for year 3. So same procedure. So it's not necessarily hard, it's just time consuming, but taking your time and getting the marks is probably better than rushing and not getting them. So it's worth doing. So this time for year 4, the percentage has fallen again to 1.35%. So the calculation now for the percentage in year 4 is 1.35 out of 100, 1.35%, that percentage of 4178.59, which comes to £56.41. Now you could carry on if you wanted just to complete the question, that's fine, but we've actually got the two figures here we need to compare, so we don't need to carry on. You could if you wanted to. But all we need to do now is compare these two and say, is the interest for year 4 more or less than the interest for year 3? Well, the interest for year 3 here is a bit higher than the interest for year 4, because this is £57 and a bit, this is only £56 and a bit. And so the interest for year 4 actually goes down from year 3. So it's less. And this is the working you'd need to show to back up your decision. You couldn't just guess one or the other and get full marks. You need to show your calculations like I've done here. Question 21. We've got a table summarising the amount spent by customers in a shop in 1 hour. So this is a grouped frequency table. So we're not told exactly how much money any customer spends. We're only told what they spend between. So 18 customers spend between nothing and £10. So we need an estimate for a customer who spends, who is in this group. So your best way to find an estimate for any group is to take the interval's midpoint. Take the halfway value between these two numbers. You can calculate it by adding them together on your calculator and dividing by 2. Some people can just work out what it is by just looking at it. So either or. This one, halfway between 0 and 10, would be 5. This midpoint, halfway between 10 and 20, would be 15. Halfway between 20 and 30 is 25. Now this final row here is almost a bit of a trick because it says more than 30. That's nobody. And so we've got all the data we need here. So that more than 30 is just meaningless because nobody spent more than £30 anyway. So what I'm going to do is just scrap that bottom row because we honestly don't need it at all. Once you've got the midpoints, we can now do the midpoint multiplied by the frequency. Because that means 18 people spent probably about £5 each on average. We don't know if it's exactly £5, that's our guess for the midpoint. So 18 people spent £5 or so, at a guess. That'd be 18 multiplied by 5 as an estimated total. So once we've got the midpoints, we take the midpoint and multiply by the number of customers in this case. So check these on a calculator to avoid any mistakes. 18 multiplied by 5 is 90. Next one, 15 multiplied by 15. 15 squared is 225. And finally, 7 multiplied by 25 gives us 175. And so since we've got rid of this row here, we can just do the grand totals. So the total number of customers is 18 plus 15 plus 7. Which comes to 40. So it's 40 customers. And the estimated total spend is going to be the total of all these rows here, this column. So 90 plus 225 plus 175 gives a total of 490. And so from these two totals, we can estimate the mean by doing £490 divided by 40, because there's 40 customers. That'll tell us the average amount spent per customer. So 490 divided by 40 comes out as £12.25, and that's our estimate for how much the average customer spent. Part B, we're actually given the actual mean amount spent for each group. So before, we actually just had to estimate using the midpoints. And so if I just put back up here to the side what the midpoints we used were, for 0 to 10, we said the midpoint was 5. 10 to 20, we said 15. So that one's exactly the same. And for this one, 20 to 30, we estimated at 25. So our midpoint for this one was slightly too high. The actual mean of these 18 customers was £4.50. Our estimate of 5 was a little too high. And here, our midpoint of 25 was a bit too high again. So because our midpoints were actually on the high side of reality, we can deduce that we overestimated. Because the actual means for each group were actually less twice than the same once. So the actual means overall were lower than our midpoints. So we overestimated. So it says without further calculation, decide whether the actual mean of the 40 customers will be different from the estimated mean. It will be different. So the actual mean will be lower. Reason for the answer is the actual mean amount spent per group was lower than my estimated midpoints. I mean, fair enough, it was the same once, that was the same as that, but generally speaking, the midpoints we used were too high, so the actual means were lower. Question 22. We've got the word identity in this one. Identity mathematically means not an equation where one side might be the same as another, but it means where both sides are always equal, no matter what the value of the unknowns. In the same way, though, I've said before that inequality symbols can be treated like an equals. This is another case of the same thing. The identity thing is a fancy word, it's fancy language. We can, in a way, pretend it's an equals sign for what we're going to do with it. And so I'm just going to scrub out the fact that it was identity in the first place. We're going to put back in, oops, it's a bit big. We're just going to treat it as an equals anyway. What we can do first of all is expand the brackets. And so 3ax plus 6, I'm just going to leave that first bit as it is. Now 4 multiplied by x is 4x, but be careful because that 4 is a minus, because it's got a minus sign in front of it. And then 4 times b is 4b. But again, if you're multiplying a minus number with a positive number, mixed makes minus. A minus multiplied by a positive gives a minus overall. On the other side, we've got 11x plus 14. And so what we need to do, what I'm suggesting we do, is have all the basic stuff, have all the familiar stuff on one side, and this weird stuff, the 4b and the 3ax on the other side, so we can compare one side to the other. So what I suggest we do next is to bring across these 4x's. Now these 4x's are minus, they're negative. So if they swap side, they'll swap sign to plus, to a positive. So these minus 4x's will become plus on the other side. So what we'll have is 11x plus the 4x we've moved, which will be 15x plus 14. And after we've moved those, on this side, we'll still have 3ax, we'll have 6, and we'll have 4b, minus 4b. We can get the numbers together as well, and so we can bring this 6 to join the 14. That 6 is positive, so when it swaps side, it'll swap sign. Opposite of plus 6 is minus 6. So then what we'll have is just 3ax minus 4b, and over here we have 15x's, and the number, well, we had 14, and this 6 is going to be taking away from the 14, so it'll be 14 minus the 6 we've just moved. 14 minus 6 would leave us with 8. It's still positive 8 because 14 take away 6 still leaves us with 8. If it was 6 take away 14, that'd be minus 8. so the 8 is positive. Now what we can do is we can have a look at this a bit more closely. So compare the x's. How many x's do we have on the left hand side of the equation? Well, we've just got 3a x's, whatever a is, we don't know, do we? So on that side we have 3a x's. On the right hand side we've got 15. Now an equal sign means that one side is equal to the other. And so we've got 3a x's on that side, 15 x's on that side. 3a must be equal to 15 because of that. The x's on that side are equal to the number of x's on that side. So based on that, just comparing what numbers are in front of the x on each side, we can say that 3a must be worth 15. We want to have just a on its own. So what we can do with that 3a is swap side and swap sign. That 3 was multiplying the a. Opposite of multiplying is dividing. And so a will be 15 divided by 3, which would just be 5. In the same way, if we have a look at the units, over here we've got positive 8, over here we've got minus 4b. So from these two we can say that minus 4b, the units on the left have to equal the units on the right. So minus 4b must equal 8. Normally I'd say to avoid dealing with minus numbers, but if you've got a calculator paper it's no problem really. We want b on its own. Minus 4b means minus 4 is multiplying the b. If there's no mathematical instruction between two different things, it will mean one is multiplying the other. And so if we swap this minus 4 to the other side, it'll become a division. So b will equal 8 divided by minus 4. So if we try that on a calculator, just to be careful without getting confused too much by all these negative numbers and things, 8 divided by minus 4 gives us minus 2. So a is 5, b is minus 2. And take it from me, that is not a straightforward question. That really is quite challenging. I suggest expanding the brackets, getting the x's to the same side. That could be a way of picking up 1 or 2 marks here. If you got all of that, then very well done. That would take, I think, more practice. It's a very rare question, particularly difficult. Question 23. We've got a right-angled triangle. We've got an angle, a side, and we want to find out another side. This question should be screaming to you, trigonometry. And when you hear trigonometry being screamed at you, 3 other things should also be screamed in your direction. And those other things are SOHCAHTOA. SOHCAHTOA. You need to remember this. SOHCAHTOA. So let's just remind ourselves of what all these letters mean. So S stands for sin of whatever angle we're talking about. C stands for cos, again with your angle in brackets, and T stands for tan of whatever angle we have in the question. So the angle we've got here is 20 degrees. You'll always have a right angle for using trigonometry in this GCSE. So work out the length x. What we need to do now is label the sides. And so O stands for opposite side. To find the opposite side, we have a look at the side which is opposite to the angle in question. Opposite side always means opposite the angle. And so the opposite side is the x. The longest side is called the hypotenuse. H stands for hypotenuse, and it's always found opposite to the right angle. You can normally just spot by looking which side's the longest by how the triangle looks, but if you're ever unsure, you can work it out for definite by just looking at what side is opposite the right angle. So in this case, it's this side, which is 12. So we can label that side H for hypotenuse. If it's not the opposite side or the hypotenuse, the other side is called the A. A, by the way, stands for adjacent. Now what we can do is we can tick off what we know. So we know H. Also tick what you want to know, which is finding X. So we know H, we want to find O. As for the adjacent, we don't know it, we don't want to know it, so we don't care about this bottom side. All we care about is H and O, because we know H and we want to know the O. So if we just highlight H for hypotenuse and see what triangles H is mentioned in. So H is in the sin and cos triangles, but not in the tan one. And whereabouts is O mentioned? Well, O's in the sin triangle. It's not in this one. But the opposite side is in the tan triangle. So we've tipped them off and we've included them in these magic triangles. Whether we pick sin, cos or tan now comes down to looking at these triangles coloured in. Which one is most colourful? Which triangle have we put more colour on? It's got to be this one here. It's the sin triangle. The triangle you need to pick, you can either think of it as the most highlighted one, or the triangle that includes what you know, H in this case, and what you want to know, which is the O. So now we can apply this knowing that we're using the sin button. So we're going to be using sin at some point. Length X is the opposite. Next, what we do, whatever you want to work out, we cover up. And whatever's left in the position it's in tells us what to do. And so O, opposite, is S and H next to each other. Two things in algebra next to each other with no instruction will always mean one multiplied by the other. So O equals S times H. But remember, what does S mean? S stands for sin of the angle you're talking about, which is 20. So sin 20 multiplied by the hypotenuse, which is 12. So X is your opposite side, so we can do this calculation now to find out what X will be. Sin 20 multiplied by 12. So sin, type in 20, close off your brackets, and then multiply that by 12 equals. So to two decimal places, for example, or three significant figures, we'd get 4.10. So the answer to this one is 4.10 centimetres. And that's our final answer for how long side X is. Question 24, last question on the entire paper. We can breathe a sigh of relief. 140 is a product of prime factors in index form. This just means doing one of those factor trees. So we start with 140. And what we do is we think, what can we divide 140 by? If in doubt, if a number's even, it can always be halved. Half of 140 is 70. And use a calculator to check these calculations as well. You don't want to be making silly slips at the end of the paper. So what we do now, if we've got a prime number, we circle it and leave it. 2's prime, so we circle the 2 and leave it alone. 70, however, isn't prime, so we can divide it again. 70 is still even, so we can half 70, which is 35. Each time we branch a number, it branches into 2 other numbers. On one side, what we're dividing this one by, on the other side is the answer to that division. So anyway, is 35 prime? Well, 35 isn't prime because we can divide 35 by 5, which would give us 7. Now 5's prime and 7's prime, and so we're done. With these questions, you're always finished, well, nearly finished, when you've got all primes at the end of each branch. The final step is just to write down the primes in order of size multiplied by each other. That's a product of primes. But index form means we need to write them as powers if possible. 2 times 2 we can say is 2 squared. There's only one 5 and there's only one 7. So that's as simple as we can do it. Before you switch off the video, I'm going to show you how you can use your calculator to do it for you as well, which is very useful to know. Now, a good calculator will have prime factor decomposition built into it. What we do is we type in the number we wish to decompose, 140 in this case, press equals. Then we do shift and press fact, which stands for factorisation. So shift fact, and it tells us what it is. So as a double check, yep, we've got it. It's always worth knowing how to do it without using a calculator anyway, but if you master your calculator, that's just one more reason amongst hundreds why investing in a good scientific calculator and learning how to use it well will pay off in the future. So that concludes the paper. That's all the questions done. I hope you found that useful, and if you've got any comments, leave them in the comments section or ask me in class. Keep practicing, keep revising, and never give up. I'll see you soon.